Thank you very much, Chano. And let me begin by thanking the organizers for inviting me to present my work at this venue and thanking everyone else for attending. Let me know if at any point there is any problem with the video, with the slides. I think you should be able to see my slides, but let me know if there is any issue. As Chano said, I'm going to present the paper Heterogeneity in Transitory Income Risk. Before I begin, the usual disclaimer: the views that I am going to express here are mine and do not represent the position of the New York Fed or the Federal Reserve System applies. So, this is a paper about income processes, right? And I have to begin by telling you what I think an income process is. The definition is it's a representation of the uncertainty about future income faced by households when they are deciding consumption, savings, labor supply, etc. There are many ways of thinking about the income process. One is, well, because they are representations of uncertainty, they are just the predictive distribution of future income given what we know today. Equivalent representation is they are the stochastic law of motion of income. So if we take the workhorse quantitative macro model of consumption, where we have an exogenously evolving income, we have a sequence of budget constraints, and we have a household that maximizes expected utility, then arguably the income process is half of what's going on in that model. And not surprisingly, because of this role in many important models, the income process is relevant for many academic and policy debates. Debates about the nature of inequality, about the design of tax policy, about how actions in the fiscal and monetary policy areas transmit to the population. These kind of questions all have an ingredient of income processes. So this is my statement about why we care so much about them. Now, the literature on the income process builds a lot on one key idea, which is, at least it dates back to Friedman. And Friedman argued that if we take a household that is a permanent income household, if we have a change in income that is permanent, this will affect consumption. But if we have a change in income that is transitory, and if markets are complete or there are savings and so on, transitory shocks should not transmit to consumption. So this tells us that we should have a model in which at least we want a distinction between very persistent and temporary shocks to income. And this is a framework that most of the literature has adopted, and I will adopt as well. There is a related observation to this framework, which is there is evidence, empirical evidence, that there are changes over time in how important how relatively important the transitory shocks are compared to persistent shocks. There are, at least for the US, many papers that document that during the 70s and half of the 80s, there was an increasing trend in the importance of transitory shocks that later stabilized, and there is some debate about what's going on today. So this is a statement about the nature and the relative importance of temporary shocks as opposed to persistent shocks changing over time. And one natural question is, can we ask the same in the cross-section? Right? So we know that these things change over time. Do they change in the population? Do we expect some households to have low amounts of transitory income and others have large amounts, for example? This is a very natural question, but it turns out that the literature didn't provide us with that many tools to address this question. So one way of reading my paper is I will provide a framework in which I can ask this question. I can give a quantitative answer to it. And I will do so in the context of panel data. So this is what motivates this paper. Being very concrete, what I do in this paper is I take standard models of panel data, and particularly models of income dynamics, and I will make them richer by allowing for new forms of heterogeneity. I will introduce, and I will focus a lot today on one particular model that I label the Heterogeneous Transitory Risk Model, or HTR model for short. And to explain how this model is new and is richer than the original model, I have to introduce the canonical one. So the canonical model says we have log earnings, which are the Y here. And these log earnings are the sum of two components, the eta, which are the permanent or highly persistent one, and the epsilon that are the transitory ones. The upsilons that you see here, because the etas are modeled here as a random walk, or it could be an AR1 or some process that has some form of strong persistence, the upsilons affect income forever. So once we have a upsilon shock, eta is permanently lower or permanently higher. So in that sense, the upsilons are the permanent shocks and the epsilons will be the transitory shocks. The key assumption of the canonical model is that the distributions of the permanent and the transitory shocks, they might change over time, but they don't change in the population. That's precisely what I was mentioning in the previous slide in my motivation, that we can say things about how these different shocks change over time, but we cannot say much about the population. So one implication of this framework is if we try to compute the relative importance of permanent and transitory shocks, it's constant in the population. Everyone has the same relative amounts of them. One measure, for example, is the ratio of the variances. The variance of epsilon IT or the variance of epsilon IT divided the variance of the other type of shock, it's constant. This is something that is quite a limitation of that framework. So what the HTR model does is it adds a new symbol, the sigma I that you observe there. It is a household-specific volatility of transitory income. And what this makes is now the transitory component is not the epsilon IT in the previous slide, is the product of sigma I epsilon IT. This I will call the epsilon tilde in my notation. The distribution of epsilon IT will be assumed to be constant in the population, but because we have the sigma I, the different households can have different amounts of transitory income. And so this is precisely the extension that I want to analyze, to ask the question that I presented in the previous slide and to give a quantitative answer to that. What I'm going to ask is how different are the sigmas of different households. So we will have households that have high sigmas and households that have low sigmas, and this will allow us to have a sense of how much inequality there is in the transitory risk. So I'm going to tell you to summarize the results of this paper in 4 points. But before I do that, I want to mention one thing about this model, which is, well, I take the standard canonical model and I introduce one variation, which is I allow the variance of the transitory component to be individual specific. Why not doing something else? Why not letting the variance of the permanent shocks be heterogeneous, or I don't know, some autoregressive coefficients or things like this? Why do I want to focus on this particular form of heterogeneity? There are 2 or 3 reasons that I can think of. The first is when we think about differences in the level of income, one thing that we know is the initial condition matters a lot for that. For the US, at least, half of the variance of income can be explained by the eta I. If we think about changes in income, not the level, but changes, and we think about the variance of changes, then the transitory component is overwhelmingly important. There is, for the US, at least something like 90% of the variance of transitory income, of income changes are transitory in nature. So because of that, I want to extend the model in the direction that is the most important, or that I think it's the most quantitatively important, and that's why I take the avenue of modeling the transitory component. Another reason is transitory income shocks resemble many policy experiments. So if we think about the COVID pandemic, and we think about what many governments did was to give transfers to households. So we think about previous recessions in the US, so we think about the 2001 tax rebates, etc. All these kind of policy changes are arguably transitory in nature, and therefore they look like transitory income shocks. So if we want to understand what is the effect of these policies on consumption, for example, one way of thinking about that question is, what is the effect of a transitory income shock on consumption? And there is a third reason, which is, well, I want to allow for new forms of heterogeneity, and I, in principle, could allow for many forms of heterogeneity, but I have to be disciplined, because the more heterogeneity I add, the more data I will need to disentangle them. So this will be actually the first result of the paper, is the more heterogeneity you have, the more time periods you need to identify this model and to be safe in estimating it. But this is a device that helps us discipline the amount of richness that we allow in the model. So I will, yes.
Hi, Martin. Just a brief question. This is Federico from the Central Bank. do you have a sense of like a motivation of what dimension you're thinking about in terms of this heterogeneity? Are you thinking that this is going to be important in terms of skills or geographical location, or what is it that you have in mind in terms of like motivating what could be sort of behind this heterogeneity that you're studying?
Yeah, that's a very good point. My way of thinking about this, my initial way of thinking about this issue was, well, we can construct models of the labor market in which we will have people having different sigmas, right? One way of constructing such a model is, well, we know that we can have devices that make people stay in jobs for long periods. Actually, in the data, we observe that people stay in jobs for long periods. So these sigmas are job specific somehow. And some jobs have, for example, different contractual arrangements because some of them are subject to agency problems. Some of them require skills that have different productivity profiles or things like this. And all of this could produce an equilibrium distribution of labor contracts that give you these different types of transitory income. So my understanding or my interpretation of this is, well, we have a model in which people have these different sigmas as an equilibrium distribution. The sigmas are a function of things that you mentioned, like skill, like the productivity profile, the nature of the job that's being done. And these things tend to change very slowly over time, and people tend to remain for long periods in the same job. And that makes this assumption that the sigma i's are constant over time plausible. As a very, very crude example, what I have in mind is, for example, a school teacher and a waiter, for example. A waiter will have a big part of the income will come from tips that will probably be transitory, and a school teacher, or I don't know, maybe depending on the country, that might not be a good example, but a school teacher will have a much safest income profile. That's kind of what I have in mind for this model. Now, having said that, I claim here that there are models of the labor market that can produce this distribution of sigmas that remain more or less constant over time, but I don't get into the details of trying to test what kind of model would produce this. I will, however, at the end of the empirical part, give you some evidence that there is some correlation between the sigmas and some labor market variables that point towards that direction, but I don't get into the task of constructing such a model.
Okay, thanks.
So the results of this paper, as I said, will be collected in 4 big blocks, and that's how I will organize the rest of the presentation. So the first is the econometric side of this model. I will discuss how this model is identified and estimated, and moreover, I want to focus here on an environment in which I have many households, but I have a few time periods. I don't want to have a lot of time periods for many reasons. The first of which is, if I have a lot of time periods, then my assumptions that things remain constant over time is less credible. So I want to have as few time periods as possible to achieve identification and estimation. One thing that I will show is this particular model, if I have 5 periods of consecutive observations and I make very, very mild regularity assumptions, it will be non-parametrically identified. If you give me the distribution or the joint distribution of income in the population over time, I will be able to give you the distributions of the epsilons, of the upsilons, and the joint distribution of thetas and sigma, so all the heterogeneity, without making any parametric assumption. This will be the main result of the paper. After saying this, I will, after showing you how this works, I will propose an estimation method that is also non-parametric in nature. Instead of saying here that it's non-parametric, I just want to say it's flexible, because there are many questions about the non-parametric nature of these estimators that are still open in the statistical literature. But the point of this is saying there will be a flexible estimation method that allows us to fit an arbitrary shape of the distributions of heterogeneity and shock distributions. And this is something that we want, because at this point, we don't know a lot about what's the ex-ante shape of this distribution. This is the econometric side. The second block of this presentation will be empirical. I will go to the PSID, which is panel data for US households. I will construct a panel of a short panel of household earnings, and I will estimate this model. And what I'm very interested here is I want to get a density for the sigma I, because this will allow me to get a sense of how different people are in their sigma I, and how different is this model from a model that denies heterogeneity in the cross section. The answer, and there will be a figure in the next slide that illustrates this, is people are very different in the sigma I's. And I will show you a picture. I will comment a little bit more later. But another thing that I can say is there might be some relationship between the sigma I and the eta I. Now, the sigma I here is the volatility of transitory income. Some households will face a lot of transitory income, like a waiter and the tips, and some households will have very low amounts of transitory income. But the eta I, which is the initial level of income, which is also a main driver of income inequality here, because it's a permanent income. It's the amount of income that stays with you for a long period until you have permanent shocks. There seems to be some negative correlation between them. This correlation is quite weak, and it seems that the relationship is nonlinear, and I will show you some evidence of that. And this is related to Federico's question. I will try to relate the sigma I to some labor market variables. The way I will do this is I will regress sigma I on some labor market variables, and I will try to document correlations with some potential explanations of potential variables that could be behind an explanation of why there is heterogeneity in the sigma I's. This is not, again, this is purely trying to document correlations that a structural model of the labor market would try to fit. I'm not trying to argue anything else there.
Tincho,
yes.
in your framework, you are thinking on this eta I not as a shock, no? It's not related to risk. It's just it's gonna be some heterogeneity, but at the initial level, that all the workers or the individuals know about this. So this is not gonna you're not going to interpret this as a permanent risk shock. This is no.
Yeah, it's at this point I will be ambiguous about this. There are two ways of going about this. If I am looking at income data, I can think of this as trying to describe the law of motion. And for this purpose, I don't really need to assume what people know and they don't know, because here we could take different stance. We could say, well, the household at period t knows eta it and epsilon it, or the household only knows yit, which is what the econometrician knows, right? At this point of modeling the income distribution, I cannot say one way, I cannot go one way or the other. If I want to relate income with choices, and that will be my fourth point, for example, if I want to relate income with consumption, I do need to take a stand on what the households know. And when I get to there, what I will say is, well, at period t, you know your eta it and your epsilon it. This has been kind of the standard with a few exceptions. The one way of relaxing this is to allow for some forms of learning. This is something that I think Wenner and Smith did in their 2014 econometrical paper. One could go the other way around and say, well, actually, the household knows something about the future that this model doesn't know, and allow for advanced information. I'm not trying to do one way or the other here. When I get to consumption, I will just take the standard, which is to say, at time t, you know all your state variables at time t. The eta its and the epsilon its are your state variables. That's what I will do. Let me quickly say what are the last two blocks, and we can go back to this point when we discuss consumption at the very end of the presentation. So the last 2 points of my results will be, one is a bit more abstract, and it's related to an econometric idea of heterogeneity versus state dependence. One thing that I want to show here is my model is capable of producing some reduced form patterns in the income distribution that actually look like if they were produced by state dependence, by some nonlinear mechanism of the transmission of past shocks. This connection is important because recently there has been some literature on trying to have more flexible models of the income process that allow actually for nonlinear dependence instead of allowing for heterogeneity. And it turns out that for many of the implications for the income distribution, they look very similar, and it's hard to tell them apart. This is unfortunate because usually state dependence and heterogeneity have different implications. for behavior, but it's a point that I want to make here as well. And the last point will be about consumption and about consumption pass-through. And this idea of some shocks that are transitory have different transmission coefficients to consumption than shocks that are permanent. This is the whole collection of results that I want to mention today. One thing that I anticipated is there will be a key figure for today's presentation that will appear twice, and it's this figure. This is the estimated density of sigma I in the population. One thing that we observe is that there is a huge mass of households that have much lower than average sigma I, so this distribution is very asymmetric, and that's what we observe there. There is a smaller mass of households that have very high amounts of transitory income. It's a small, something like 1/6 of the population have very high amounts of transitory income. In this figure, I also draw this line at 1. This is actually the sigma I is normalized so that the mean of sigma I square is 1. So a model without heterogeneity will tell us, well, all the sigma I's are a mass point at 1. So the line and the curve are the comparison between the canonical and the HTR model implications for heterogeneity in transitory risk. So regarding literature, I want to go very quickly about this. There are at least 3 literatures that are very huge and mature and are connected to what I'm doing. One is the literature on nonparametric identification and a literature on nonparametric panel data estimators. I will comment when I get to there what are the key connections with my paper. And of course, there is a huge literature about earnings dynamics that I want to skip now. But there are some work that are quite close to what I am doing. There was a paper by Chamberlain and Irano in the, I think this is the Annals of Economics and Statistics, that they presented a model that was very similar to mine. There are 2 key differences. One difference is they don't allow for a nonparametric analysis of the model. The other is they assume that the eta I is independent of the sigma I. I will not make this assumption, and I will emphasize why I want not to make this assumption later. And then there are connections with the nonlinear transmission and consumption pass-through literature that I will get to at the time. So I want to make a small pause here to answer questions if there are any. And if not, I will start with the identification and estimation part of the paper. Okay, I will start with the econometric analysis. So here is the model with a little bit more of detail. One notation that I will use a lot is this MATLAB type notation where I put the column and 2 indices to say this is a vector with column or row, not super precise, of observations from yi1 to yi2. This is what this means. I will use this notation a lot, but it's a bit confusing sometimes. This is what we assume we observe. Either we observe data on a sequence of consecutive earnings observation, or we know the joint distribution of this object. These are the kind of framework that we have. We don't observe the etas, we don't observe the epsilons, and we don't know what sigmas and the eta I are. And that's what actually we are interested in. So as I said, I will take the random walk assumption for the eta I just for simplicity. This could be extended in many ways, but I want to keep things simple here. And the assumptions are, well, there is a joint distribution for the eta and sigma. This P of eta and sigma will be what I will call the heterogeneity distribution, and it's a key object. Here is all these statements about inequality of levels and inequality of risks can be answered with this object. And then there are distributions of shocks, of permanent shocks, the P epsilons, of transitory shocks, the P epsilons. 2 assumptions. One is an assumption of mutual independence. The eta and sigma as a vector, they will be independent of the shocks, and the shocks will be independent over time. This is something that we need to discipline the model. One thing that I'm not assuming, and I think I will rephrase later, is I'm not assuming that the eta is independent of the sigma. They could have correlation between them in principle. So this is something that empirically is very attractive. And finally, I need some normalizations. I will assume that the shocks have zero means and the initial eta I also have zero means. This is not super restrictive because I could have constants and remove mean effects or remove the effect of covariates or things like this. One thing that I have to elaborate on is this normalization restriction. I need to say something about the sigma I, its position, where it's located, because otherwise what I can always do is I can take the epsilon, multiply by a constant, take the sigma, divide by the same constant, and get exactly the same data. And therefore, the location of the sigma is not pinned down. So here what I'm saying is, well, I will take the expectation of sigma I squared to be equal to 1. Alternative normalizations would be some of the epsilons have a mean equal to some known constant. There are many ways of normalizing things, but here this is the most convenient one. And it's without loss of generality. I can take one normalization and undo it and get back to another normalization. So as I said, the objects of interest are the joint distribution of heterogeneity, the eta and sigma, and the distributions of shocks. These are essentially all the parameters that this model has. As I said, I want here to have the etas and sigmas potentially dependent of each other. It's important that they are dependent in a general sense, because as you will see empirically, it turns out that the correlation between them is low, but there is some form of nonlinear dependence between them. And one reason why this is important from a substantive point of view is, well, we don't want to rule out a situation in which, for example, low-income units, low-income households are systematically subject to larger amounts of risk. This is a very important subset of the population, because if this is a large amount of the population, we know that low-income households usually don't have the means to insure against transitory shocks. So if we are doing welfare calculations or if we are analyzing inequality in consumption, this kind of subpopulation will matter a lot for those results. So we don't want to rule out that by assuming that the etas and sigmas are independent. And one thing that I will mention briefly here, and I will come back at some point in the estimation, I think, is one could allow for exogenous covariates. One could allow for education, for age, for family structure, for all these kind of things that we expect would predict differences in the sigma i's and the eta i's and the distributions of shocks over time. At this point, because I want to focus on, I want to present the identification argument in the cleanest way I could find, I will abstract from them. We could think, well, we are analyzing households with a particular set of covariates, and we are conditioning on the covariates, and then the identification argument will go through if we just not condition. So that will be, here we will abstract for a few slides of the covariates. So I will start now analyzing the identification. If there are no questions about the framework, if there are questions about the framework, this is a good time to make them, or I could come back to these things later on otherwise. So identification in the canonical model, in the model without the sigma i's, for a long time has focused on the variances of transitory shocks and permanent shocks. And the reason is, well, they are, however crude, a measure of how dispersed these types of shocks are and how important they are and how their importance changes over time. So the variance was the initial focus. I will focus not just on the variance. I want to identify the whole distribution, but it's instructive to start with the variances here. Imagine that we have only two periods. We observe income today and income in the next year. And we know the distribution in the population of this, and we know the variance matrix in the population. So here, this object is known, is assumed to be known. We have the variance of y1, the variance of y2, and the covariance between the y1 and y2. We can write that variance matrix in terms of the variances of the latent variables. The latent variables here, the sigma eta, the sigma epsilon 1, and the sigma epsilon 2, and u epsilon 2. Here are all of them. We have three equations here, but we have many variables. We have the sigma eta, the sigma epsilon 1, the sigma epsilon 2, and the sigma epsilon 2. We have four variables. So we cannot solve for all of them, at least not from the variance matrix, but we can do our best and solve at least for three linear combinations of them. It turns out that the sigma eta can be recovered from the covariance between y1 and y2. The sigma epsilon 1, we can go to the variance of y1 and subtract our estimate of sigma eta, and we can only recover this sum of sigma epsilons and sigma epsilon in the second period. This is always the case for this model. The last period, we cannot disentangle the permanent from the transitory, but at least we know something about the sigma epsilons and the sigma epsilon 1 and sigma eta. If we had more time periods, then we can identify more of the sigma epsilons and sigma epsilons, and again, the last period, just the sum of them, by the same argument, the same type of calculations of subtracting things from the variances and covariances. But one observation that we make here is from these calculations, there is nothing about the sigma I. The sigma I is missing there, and it turns out that there is no way to learn anything about the sigma I by looking at variances and covariances of the levels of earnings, not even the levels or changes in earnings. There is a point made later that we can go to higher order products of things and learn something about the sigma I, but not with the standard moments used in the canonical model analysis. One could change the normalization. Here it's true that the sigma I square disappears because we said the expectation of sigma I square is equal to 1. We could undo this, and then we would have the expectation of sigma I square there. But the thing is, the expectation of sigma I square is not what we care about. We want to know how different people are, and one measure is the variance of sigma I, not the expectation. And the variance, it's never there. It doesn't matter what we do, it's not there. One message of this is we cannot just, if we take the variances and covariances of income and we think they are generated by this model, we don't learn anything about the sigma I square, which is one very interesting object. Another observation is, can we do the traditional non-parametric identification arguments in this model? In this model, even with 2 periods, we could recover the distributions of the eta I and the epsilon I by doing an argument by using a technique developed in a paper by Kotlarski. Here it doesn't work because the sigma I is bouldering there, but it's not, even though it doesn't show up in the second moment. So what we need to do here is take a completely different approach to linear model identification techniques. And what I will do is I will use an analogy with a measurement error problem. Given that I will identify the distribution, what I will do in the following slides is say, well, if we have 5 periods and if we make some regularity assumptions that are very, very mild, we can recover all the distributions that we care about. In particular, we can recover some objects like the variance of sigma I, the covariance of eta I with sigma I square, and all these interesting objects. But we cannot use the standard techniques for identification here. So one slide detour to give the intuition of how the identification is achieved in my paper is here. Imagine, forget about the HDR and income processes for a second, and just let's focus on a standard measurement error problem. We have a regressant Y that we care about. We have some latent X star that is like a regressor of interest that we don't observe. Instead, we have a noisy measurement that is X, and we have some instruments, or they could be alternative measurements, C. This is a very standard basic econometric problem, an instrumental variable treatment of a measurement error problem. There are exclusion restrictions that are needed, that are always in this kind of problems. One exclusion restriction is, well, if we knew the true measurement, the X star, then Y would be independent of X and C given X star, because the X and C have no relevant information for Y beyond X star. This is something like assuming the errors, the measurement errors in the X and C independent of the X star. And then there is the other assumption that the X and the C should be independent given X star, which means something like the measurement errors in X and the measurement errors in C, if they were alternative measurements, they would be independent of each other. So this is like the standard two-measurement measurement error problem, in which you use one of the measurements as an instrument of the other in the regression. But here we are not happy just with a regression coefficient. We want the whole distribution of Y given X star. This problem has been recently studied, how to recover the distribution of Y given X star when we have all this framework. Under very general assumptions by Hu and Shenak, what they say is, well, there are 4 assumptions that I will not mention now, but there is a key assumption that they say, if there is a functional of the distribution of x given x star, the distribution of x given x star is like the distribution of measurement error in the noisy regressor. Right? If there is a functional of this distribution, some way of taking this distribution and doing integrals, doing expectations or things like this that pins down x star and some other regularity conditions, then we can recover the distribution of y given x star. Right? And we can also recover some other distributions like x given x star, which is a distribution of measurement error, and so on. This seems to be very far from the model that I just described, but actually it is not. There is a very clear analogy. So here the non-parametric identification problem, coming back to the HTR model, is we want to recover all these distributions of heterogeneity, of shocks, etc., from the distribution of observables, which are the y1 up to yt. And imagine that we have five time periods. Let's begin not with this full object of all the distributions, but the joint distribution of eta3 and sigma I, eta I3 and sigma I. We have 5 periods. What I would do in that case is I will take the middle income, the income in the middle period, the y3, as playing the role of the regressant. I will use the eta I3 and sigma I as the regressor of interest that we don't observe, but we'd like to. And then I would use the future income as the noisy measurement and the past income as the instruments, or as an alternative noisy measurement. The exclusion restrictions that are always in this instrumental variable treatment of the non-classical measurement error problem, they are implied by the fact that eta it is Markov, is first order Markov. One can check them. But the key assumption in Hu and Shenach is from the distribution of yi4 and yi5, which are the noisy measurements, given the eta3 and sigma I, which are the latent variables we want to recover, we can do integrals and calculations that give back the eta I3 and sigma I. And it turns out that the eta I3 is just a conditional expectation, and sigma I is some function of some conditional variance. And here the sigma epsilon4 and sigma epsilon4 can also be written in terms of the data, because this was the matrix that I showed at the beginning.
So in terms of Hu and Shenach, the difference here is that you have like 2 latent variables that could be potentially, well, that are actually endogenous. So you need 2 instruments.
Exactly. Yes. That's exactly the rule that is here. If we had 3 sources of heterogeneity, we'd need 7 periods because we'd need 3 noisy measurements, 3 instruments, and then the middle period. If we have 4, we will need 5, and so on. This is kind of the rule that comes up from here, provided that all the other completeness and regularity conditions hold. Here, however, we identify certainly the distribution of eta3 and sigma. It's not exactly what we want. We want eta and sigma and all the shock distributions, but by doing Kotlarski, I think 100 times, you get all of the other distributions. Once you know these 3 distributions, these other distributions are a pretty standard problem. You just condition on sigma, and it's a linear model. So it's quite easy to get all the distributions. So the theorem here is, if we have at least 5 periods, and there's some regularity conditions that I'd rather not get into, we can recover all these distributions. One thing, as in the variance matrix calculations, the last distribution, the epsilon capital T and the epsilon capital T, cannot be disentangled. We can get the distribution of the sum, but that's not very interesting. But it's just because even the variance cannot be identified. It's not a problem with this model. It also happens in the canonical model. But the important thing is we can recover particularly this object, the joint distribution of heterogeneity. And as Chano just mentioned, we have this rule. If we had a k-dimensional heterogeneous object, we'll need at least 2k plus 1 periods to identify this model, using my argument. One question is this a necessary condition? Because all these are sufficient conditions at this point. Here is all these conditions are satisfied, then all these distributions are identified. But can we say the opposite? Can we say if the distributions are identified, then for sure you must have at least 5 periods? There is one situation in which the answer is yes, and this is when you don't have stationarity, when you assume that the epsilons and epsilons have distributions that potentially change over time, and when you have a non-shaped distributions for the shocks. for the shocks. I mean. If the kurtosis and the skewness of these shocks are not known, for example, if we don't say the shocks are normally distributed, which is for the epsilons at least a bad assumption in the US data, then this condition that T has to be at least 5 cannot be relaxed. We could relax, actually, I think that there was some paper that discussed, now it doesn't come to my mind the name of the author, but there was a job market paper that discussed the case when you have assumed normality for the shocks and you could relax a little bit this T equal 5 period.
Tincho, one curiosity. If this condition about the number of time periods and the amount of heterogeneity you can allow also relies on the Markovian assumption that you use for the persistent shocks, I was thinking that the Markovian in some sense is what is giving you relevance. But if, for instance, you start with a model that is not a unit root, is an AR1 with persistence, and maybe in the DEP, the real persistence, the raw parameter is 0.5. In that sense, at some point, if you want to allow for more heterogeneity, under the assumption that you have a higher T, capital T, there is some point where the relevance could break, in the sense that maybe if there is not so much persistence in the earning dynamics, maybe you cannot have still building instruments.
I think, yes, I completely agree with this statement. Here, one could relax the random walk, could say, well, we have, I don't know, an AR1 with 0.2, which is a very low amount of persistence. Any amount of persistence above 0 would work for the identification argument, but most likely, because in the identification argument, we have a huge advantage, that is, we know the joint distribution of income. Most likely, when you go to estimation, you will have problems there, because you will run into some form of weak IV problem. I think that's what you have in mind here, and I completely agree. The random walk assumption for this argument is not critical. One could relax that. If you have heterogeneity, if you have autoregressive coefficients that change over time, maybe you need one or more periods to identify the coefficients in the middle. But I agree that if the persistence is very low, at least there will not be so much information between the Y1 and the Y capital T. There will not be so much common information between them, and this could be a problem mostly for estimation, because this is the same as in weak IV. In weak IV, you can have a ridiculously weak instrument, and when you only think about identification and you fix the predictive power of the instrument, you still have identification, but then you go to the data and it doesn't behave so well. Right? So I think that would be my reason of what's going on there.
It wasn't like a critiques to the identification. Actually, it was more the
I completely agree with this.
My point was more for estimation. Right.
I will now talk about the estimation for the income process application that I have in mind. The income process usually is very persistent. There is no, I don't know of any data set in which income is not, it doesn't have this close to random walk component. What could happen, however, is that this model is very hard to test against a model in which you have a very low persistent shock for a very low persistent component, but you also have something like a linear heterogeneous trend. These models are hard to distinguish, at least in short panels, and they are alternative ways of adding heterogeneity. I guess for that kind of model, actually, it could be a big issue. This issue of the lack of persistence. But for this one, at least, I am quite confident. But yes, completely, I take your point. This is a very good observation. Let me quickly say what I do with covariates, because for the empirical analysis and most of the time when we construct these flexible panel data models, we want to have covariates, at least exogenous covariates, entering somehow. As I said, in this income process application, we want to have age and education and family composition at least, and maybe geographical location, because we expect there to be a life cycle in the earnings process, and we expect also households to know that there is this life cycle. So we don't want to attribute everything to the latent variables, and we want to net out the effect of this covariance. So what I will do is, for the identification, what one could do is we could let the mean of the YIT given the exogenous covariance be a flexible function of xi. This is identified non-parametrically because the mean of YIT given xi is exactly mu it xi, the function that you observed there, mu t, sorry. And then we could let the etas and the epsilons and upsilons have distributions conditional on x. All I am going to ask is that the independence and the normalizations that I introduced when I described the setup, they are holding for each value of xi. So in particular, we need to have this assumption that the expectation of sigma I squared given xi for every value of xi is equal to 1. This is still like a normalization assumption, but it's more in the like a random effects type of assumption as well. If we do this, one thing is that the theorem goes through just without changing a word. All you have to do is just add the xi's everywhere. It really complicates the notation, but doesn't change anything. We can always just condition on xi, and everything goes through there. But now I want to start discussing estimation. In the estimation, the message of the identification theory is we could have, in principle, one different assumption for eta I and one different assumption for sigma I and for the epsilons and upsilons for every value of x. But usually we don't have so many observations to learn about this in a very free way. So what we need to do is, at least for the PSID and even for administrative data, we want to have some discipline here. What I will do is not assume that the distributions of eta i's and epsilon i's and epsilon i's, they are completely arbitrary given x. I will say that the x's, the exogenous covariates, enter only through the means and variances here. And then once we standardize variables, then these new variables will be independent of xi. So their distributions in particular will not have xi anywhere. This is important because what I'm ruling out here is the asymmetry of the shock distributions and the kurtosis and things like this. They don't depend on xi once we standardize them. But I will let the variances and the means, which are quite important objects here, to depend on xi.
So it's a model just with conditional heteroscedasticity.
Yes.
Sorry, go ahead, Tincho. Sorry.
No, I was going to emphasize the model with full distributions dependent on xi is identified, and we could come up with a more flexible way of interacting covariates and latent variables. But here I took the decision not to relax things further because at least the PSID will not like it for that purpose.
And yes, I'm now talking about in terms of the estimation strategy. Another curiosity that I have is, I guess what you're gonna do first is you're gonna get rid of the covariates, and then you're gonna think on the residuals as the income shocks or income risks or something like this. When you do this, are you allowing for some of the covariates, for instance, education and variables like that, to be correlated with the unobserved heterogeneity, with the eta, for instance?
That's an issue that is here, that is everywhere in the literature. It will not be correlated because what we are assuming that the normalization, now it's like a random effect. So this is exactly why I mentioned this. The expectation of eta given x, all the x's that we have, is equal to 0, and therefore the eta is mean independent of education, it's mean independent of age and other things. So they are not correlated. And the same with the sigma I. The sigma I is not correlated. So one way of thinking about this is, well, the eta I is some form of residual, the eta I and the sigma I, they are some form of residual heterogeneity. This is not different to the way of thinking in all the literature, right? All the netting out is you remove some constants, some intercepts that depend on covariates, and then you think of the rest as if they were independent, completely independent.
So you're not thinking, no, I am not gonna, I know that this applied to all this literature. Just trying to see if this literature is thinking about eta as a heterogeneity skills or something like this. Because if it's heterogeneity skills,
you would like it to be correlated, right?
Correlated, yes. To have a fixed effect approach rather than random
exactly,
effect.
Exactly. It's precisely because of that I mentioned the random effects. I made the random effects comment. Here, it must be uncorrelated with them. It must be for identification, actually. It's I mean, there are some things that you could identify in the fixed effect version where you let the distribution of eta and sigma given x unrestricted, but it's not. I mean, the kind of objects that you can identify there is not really. It's not as interesting as the kind of objects that you can identify here. You have the caveat that, for example, if you think that the eta I that has the interpretation of skill would have some component that is a function of xi. That component is just wiped out here. The same with the sigma I. Right? It's one limitation to the interpretation of what we're getting from here. And also because this is flexible or non-parametric analysis, one way of thinking about this is, well, we first start with the random effects assumption, and we get these etas and sigmas that we know are completely net of these skill effects or life cycle patterns or things like this. And then we try to model things, or maybe bring in some external data to reconstruct the part that we removed. I think that would be one way of going here that would work and maybe give interesting things. But starting from the random effects, from the fixed effects perspective, usually leads to not much. And I'd say not this model, but I remember that the model with heterogeneity in the autoregressive coefficient, for example, is only partially identified in that case. If you have the fixed effect random coefficient type assumption. So that's the fixed effect version of this is quite complicated. So my preference would be to go first from the random effects and then trying to do the reconstruction if possible. I want to be very brief on the estimation, the details of the estimation, because I want to get to the data now. So now we have some mean and variance functions that depend on covariates. I will model them as flexible series expansions. It turns out that we can do conditional means and variances of the y's and given x, and these identify all these coefficients in this series expansion. So here we can think of these as linear regressions or polynomials and things like this that approximate the flexible functions of covariates that we'd like to have. For the standardized latent variables, these no longer depend on the xi, so I need to model their distributions only. Here there is a joint distribution, which is the sigma I and the standardized eta I. And then there are these marginal distributions. So I model them in terms of their quantile functions, and I do splines with exponential tails. We can think, there are many ways of doing this step. We could do distributional regressions or other approaches to sieves, like mixture models or things like this. Here I took this approach that gives a very convenient estimation algorithm, but there is no obstacle to doing different things. The important message of these two slides is we have a flexible model for the functions of covariates, the way the covariates enters into the mean and variances of latent variables. And we also have a flexible representations of the distributions of the latent variables. And there is a very convenient and easy to implement algorithm for estimating things. This Chan anticipated a little bit what I do with the observable heterogeneity. This part can be estimated by doing ordinary least squares and nonlinear least squares, and it's quite fast and reliable. And once we estimate the beta, we go to we construct this. Well, we don't observe the latent variables, but we can draw them, so we can do something like a stochastic EM algorithm to estimating the gamma here are the parameters of the distributions of standardized latent variables. So this is like a two-step estimation algorithm for first estimating the part that comes from observable heterogeneity, and then all these latent variable distributions in a flexible manner. There is about the inference theory, I want to be very brief because this is something as I said at the beginning, the statistical literature still is quite open about what happens here. I know that for this particular estimator, you have non-parametric consistency, but this is not a super strong statement here. If you have the flexibility of the models going to infinity at a certain rate, and you have the number of households tending to infinity, and this is fixed, you can have these nice statements about the estimated distributions and the means and variance functions tending to the true functions. This is kind of the idea here. And it's reassuring, but it doesn't tell us anything, or it doesn't tell us much about inference. So I want to skip the part of inference because I'm running out of time, and I would like to go to the empirical part. So regarding the empirical analysis, first, the data that I use is the PSID. This is a panel study of households in the US that started very early. I think 1968 is the first wave. In the recent waves from 1999 onwards, the data is collected every 2 years. And on top of income data, we have consumption and wealth data and a lot of other variables. So that's the one I'm going to use. Instead of using 5 periods, I will use 6. And the reason for this is for comparability with some other estimation, some other estimates in the literature. But I could use 5, but here, just for comparability, I want to use 6. One thing is, what is income here? I will consider labor earnings and transfer some taxes for my household analysis. Here, what I'm doing is I understand as a household a collection of people that the representative person, what is sometimes called the head, is always the same and satisfies some constraints in age, in gender, marital status, these kind of things. And I defined as income the disposable income of the household. That's what I want. Why do I want to focus on this measure? Because this is the measure that is most relevant for understanding consumption choices, and I want to do some calculations with consumption as well at the end of the presentation. An alternative analysis that is done in the paper is I construct a panel of workers. Instead of just asking the family to have all this structure, I focus on the representative person and on the wage of that person, not considering the part of hours and participation and all this. And these estimates of sigma that I obtained there and the distribution, they are not qualitatively very different from the household exercise, but these ones are the ones that I want to have to relate to labor market variables, because labor market variables are at the worker level, not at the household level. So these are the kind of 2 broad exercises that are done here. I think there is a question.
One question, Tincho. How do you treat the periods where a household exit and entry the labor market? So did you treat this as shocks, as persistent shocks, or you complete abstract from these?
I abstract from so in my first estimates that I'm going to show now, I will not take a stand on what they are. I will just say, give me the income data and don't tell me anything else about these people, and I will do my estimates. And then maybe we can compare what happened to them. This I do in the second exercise, and there is one table that I'm going to show you about that. Not for the purpose of the shocks themselves, but for the purpose of relating the quantity, the amounts of quantitatively to relating the sigma i's with other variables. Because one way of thinking about the sigma I is, well, it's mostly driven by people that go in and out of the labor market very frequently. That's one type of job that features a lot of transitory shocks. It will turn out to be the case. That's the best predictor of sigma. It's not that it predicts everything, but it predicts a lot of what happens with the sigma I. At this point, I don't use anything else, and I don't include the labor market variables, for example, changes in employment status. Although I have that data, I don't include them in the covariates. What I include in the covariates are things like unemployment, age, education, and family structure. I come back to this after the table, actually. So what I'm going to show quickly is this figure you have seen already. It's the same figure as the beginning. One number that I want to cite here is what are the cumulative probabilities here. A model without heterogeneity would say everyone has variance, sigma I squared equal to 1, the line that you observe there. The estimates from US data are there is half of the population that have 0.5, so less than half of the average variance, and there is 1/6 of the population that have 2 or more, so twice the average variance or more. So these are very, very different to the representative person in the canonical model. That's one number that is related to this picture. One additional exercise that I can do now, because I have covariates, is I can construct a total measure of transitory risk, which also includes some average of the variances of the epsilon t's. The variance of the epsilon t's depend on covariates. So here what I'm using is like the sample distribution of covariates, and I'm averaging that. So what you observe is the shape of this distribution doesn't change much when you go from just pure heterogeneity to adding covariates. That here covariates include, as I said, education, age, and family structure. So the shape is exactly the same, and all these probabilities that I mentioned comparing to the average, they don't change much from the exercise without the observable heterogeneity. And this is a symptom that actually the unobserved heterogeneity drives a lot of these differences. If you do some type of R-square calculations that here, they are not so straightforward because things are not linear anymore, you get that there is a very small fraction of these sigma tildes, which is the total amount of transitory variation that can be explained at least by education, age, and family structure. This might be related to what Chano, and I think a question that was at the beginning by Federico, mentioned, that this dispersion, actually we should expect it not to be on the side of family structure or these kind of things, but to be on the side of skill and the type of work you do. And I think in 2 slides I will have a table that points to that. Well, actually this figure is very hard to read. I should delete it, but I always forget. I want to show this. This is what about the joint distribution of etas and sigma i's? One thing that I could do, because I can estimate this joint distribution in a flexible manner, I could recover things like the quantile functions. I can fix the eta I, for example, say I will take someone in the 10th in the first quintile of income or decile of income, and look at the distribution of sigma I given that people. So if doing that is equivalent to drawing a vertical line here and looking at these 3 lines that you observe there. This is a 25 percentile of the sigma I square distribution given eta I. This is the median, and so the 50 percentile, and this is a 75. So here you have 50% of the sigma i's corresponding to an eta I of, well, 0.2 is the quantile, right? In the 20% lower part of the distribution. What we observe here is for the middle of the distribution, there is quite a lot of variation, and it's quite stable, actually. There is some evidence that in the tails, particularly in the lower tail and the upper tail, you have a little bit more of this systematic relationship. So people that are in people that are in the very low part of the distribution, in the very high part of the distribution, they tend to have a little bit more of transitory risk than people in the middle. One story that is compatible with this, but at this point, as I said, it's purely speculation. I'm not trying to make a structural labor market story. Is here you have like low-paying jobs that feature a lot of transitory risk, like as I said, a waiter. Here you have the middle-paying jobs that feature low amounts of risk, and then you have the stock market broker that sometimes get a bonus, and then a lot of transitory, a lot of transitory income. Well, and the shock distribution I wanted. This is the table that I mentioned earlier. One thing that I can do is I can take the sigma I. The sigma I is not observable, but I will explain how this can be done, and regress that on some labor market variables. I didn't include the labor market variables in the netting out exercise, so they are not part of the sigma epsilon, because if I did that, they would be orthogonal. Here they are not. So this is just trying to obtain these correlations between the sigma i's and these alternative regressors. what we observe is that actually unemployment and self-employment, which are indicators of this phenomenon of going in and going out of the labor market, they predict, they have a lot of predictive power for the sigma I. Actually, it's in the sign is positive, meaning that if you are, this variable here is the frequency of unemployment in a given year. So in my sample, everyone is employed at least a little bit, but some people work the whole year and some people spend some months unemployed. And the same with self-employment. If someone goes frequently into unemployment, and this is more of a story of types than a story of shocks, as what Chano was saying. If someone is of a type such that gets to unemployment very frequently, this predicts a high sigma I. That's essentially what this table is saying. There are some other patterns that kind of make sense, like some industries are safer than others, and some occupations are safer than others. For example, a clerical worker is much safer than someone who part of the income depends on the performance of sales. These all make sense, but these things are much weaker than this prediction of unemployment and self-employment. So that's a very quick review of the main empirical evidence in the paper. I want to make the last two points, which are about state dependence and about consumption. And I want to go quickly on them so we can have some time for discussion. About state dependence, before state dependence, actually, I want to say something about model fit. If we go back to what I said when I was talking about identification, I said when we take the variance matrix of income, we don't learn anything about sigma I. We just learn about the usual things, but sigma I is not there. What we could do is we could take income changes. We could take delta YT here is just YIT minus YIT minus 1. We could square them, and we could try to compute variances and covariance. We could do this type of higher order covariance matrix. And it turns out that these things do tell us something about the variance of the sigma I square and the covariance between the etas and the sigma I square. So they tell us something about the distribution of the heterogeneity. They also have an implication that is this number should be constant over time. So we could do this with different periods, with different T and S here. And then if we try to go to the data and construct this variance matrix, we should observe these numbers to be always the same. And this is a prediction that we can test. So what I did was to do a specification test. So this is just testing that some moments are equal. It's not a non-standard testing problem. And well, my model is not rejected, but there are some technical discussion here about whether this test will behave well. And even if you do the test in what I think is the right and refined way, you don't reject the restriction. The alternative hypothesis of this test, and I'm going to show you two tables now that kind of give you the why it doesn't reject. The alternative hypothesis is there is some pattern in these higher order covariances that it's not constant over time. Maybe it's decreasing over time. These stories of decreasing things over time usually have to do with state dependence. They are not fully implied by state dependence, but if you have some forms of state dependence, you'd expect more correlation in the near future, and then less correlation going forward. This doesn't happen here. This is, for example, the first element. So here I'm using, again, the 1999 to 2009 data to compute these correlations between the delta y IT square and delta y S square. This is something like a fourth order moment, and it's this variance here. So the three numbers that I put here, they should be constant, or they should be more or less constant. Actually, they're estimates, so they will be noisy, but they should be more or less constant. And they are a measure of the variance of sigma I square. One thing that here, it seems that this one is quite outside that range, but actually the standard error for this would be quite large because these are fourth order moments. So this is why the test doesn't reject here. If you do these calculations in a refined way, you get an estimate of the variance of sigma I square that is somewhere in 0.6, 0.7. It's in line, but it doesn't need to be with the non-parametric estimates. So there is, just by looking at these covariances, you see that there is evidence in this data set that there is the evidence that is compatible with the story of a constant sigma I. This one is the third order moments, these covariances of delta squares with y's. This tells us something about the covariance between the eta I and the sigma I squared, the two sources of heterogeneity. And here what you see is not very, it's in line with what I showed you earlier. These numbers tend to be very close to zero. If you put a standard error, actually you don't reject that they are different from zero. And it's a measure of the covariance or the correlation between the eta I and sigma I squared. It's not surprising after seeing the estimates that I showed you that the correlation is close to zero, because we have this first decreasing, then stable, and then increasing pattern in the relationship between sigma I and eta I squared. This says that there might be a relationship. If that relationship is there, it's quite nonlinear, and this is exactly what compatible with what I'm showing here. And what is important from the point of view of diagnostics of this model is these numbers are not too different from each other. So this is that these numbers are similar to each other, and that these numbers are similar after you consider estimation uncertainty. Is a reflection that this model is not rejected. But this is not enough. I mean, it's good news that the model has restrictions that are not rejected by the data. But one thing that is particularly important here is, imagine that I simulate data from my model, and then I try to run some flexible quantile autoregressions of the income data of today's period against yesterday. So I want to have like an arbitrary joint distribution, conditional distribution of yt given yt minus 1. This 3D plot that you observe there is a measure of persistence in the yits, not in the etas. The etas have constant persistence because they are random walk, and the epsilons have zero persistence because they are white noise given sigma I. But when you go to the y's, you have a pattern of changing persistence. If you are here, for example, a low-income person and you have a very good shock, then the persistence goes down. And the same if you are like a very rich person with a very bad shock. And this is very similar to a story that that is underlying the current nonlinear persistence model of income. There is an alternative, which is here, a way of thinking about income, in which you say, well, the eta it is some flexible function of eta it minus 1. So it is not exactly an AR1 with a constant coefficient or a random walk. It's something more flexible. And in particular, it might be that the correlation between eta t and eta t minus 1 depends on the shocks that you have and eta t minus 1. This is precisely you are rich, but you suddenly lose your very good job, and then your future history is very different from your past history, or you are very poor and you get the lottery, something like this. This is, of course, then we could think about, I don't know, job ladder models and things like this that have less extreme versions of those mechanisms. This kind of model produces a picture like this, but my model that has no linear dependence pattern whatsoever also produces this. So it means that when it comes to the reduced form evidence from nonlinearities in the income distribution, it's very hard to tell apart these two stories, one about nonlinear transmission and one about the heterogeneity. And this is not so uncommon in econometrics. It happens also in duration models, in linear panel models. We always have this debate between heterogeneity and state dependence. There are ways to address this question, but I don't think they can be answered just by looking at income data. You will need to go further, or you will need to construct models of the labor market that produce one thing or the other and test those primitive implications, or bring in some other data that can help you tell them apart. But just by looking at income data, my take on what's here the best approximation, if it's a nonlinear transmission story or if it's a heterogeneity story, it's not it's a very difficult question. And the final point, the final block of the results of this presentation is about consumption pass-through. As I said, the PSID gives us some data about consumption. So one traditional exercise that has been done, I think at least has been pioneered by Blandel, Pistaferri, and Preston, is to regress changes in consumption in income shocks. This regression, I mean, the income shocks are unobservable, but you can do it by doing variances and covariances. Why is this regression so interesting? Well, we could try to, because of the Friedman idea that we should expect permanent shocks and transitory shocks have different implications. And these coefficients, the phi and the psi that you observe there, they matter a lot because, as I mentioned at the beginning, if we are thinking about a policy that has effects that are similar to a transitory shock, then the impact of that policy on consumption should be the psi, or should be close to the psi, probably scaled by some number. So we want to get estimates of phi and psi because they will allow us to understand what are the potential impacts of policies and what are the potential consequences of changes, I mean, autonomous changes in income. One could do many things. I mean, this framework has some limitations that I will skip now, but I want to revisit this question now using the heterogeneous the HTR model. And one reason why I want to do that is because if you just take the canonical model, and this was actually the result in Blandel, Pistaferri, and Preston, and you try to quantify how important are the transitory shocks, you get zero. You say the transitory shocks simply don't transmit to consumption. And the implication is, if you think about how well insured are households against transitory shocks, they are very well insured. That's the take. But these numbers, this zero there is quite puzzling, because if you look at quasi-experimental evidence on tax rebates, for example, you will see that people actually react to transitory changes in income. If you look at the current consumption literature, what you would conclude is people that differ, there is a lot of heterogeneity in marginal propensities to consume, because some people don't have liquid wealth to insure against them. So why should we get a zero here? My model allows us to do the same calculations, but now being very sure to control for heterogeneity. And one way of intuitive way of thinking about this is, I know that the epsilon IT is not endogenous. I mean, it's not affected by the sigma I. It could be that the sigma I here, this is sigma I times epsilon IT. The sigma I could be correlated with the non-income shock, because there could be heterogeneity also in the consumption function, and that's a danger to the just doing OLS here. So what I could do is I could use the epsilon IT as an instrument of the epsilon tilde IT. That's the intuition of what's going on. Things are a bit more complicated because these are latent variables, but that's exactly the intuition. And by doing this instrument, this epsilon IT is orthogonal to the non-income shock, even if there is heterogeneity in the income function, in the consumption function. And when you do that, you get actually a positive response that is more in line with the consumption literature and the quasi-experimental literature. This point is quite interesting, because although I'm not claiming here that this is the explanation of what's going on, it tells us that it's important to take into account potential joint heterogeneity in consumption and in the income process. There are some other papers that exploit this idea of for example, heterogeneity in patients and heterogeneity in income risk to derive things about the wealth distribution, and there seems to be some results that are very clear there. When it comes to consumption, there are other ways of explaining this gap, and actually there is a recent paper by Como about this gap that uses a completely different explanation. What she argues is we should have past income shocks in the consumption equation because the approximation from the Euler equation is not perfect. So this is not the only explanation for why there is a gap, but it's one explanation that can be discussed in the context of this HTR model. So I want to conclude and very quickly, and then perhaps we can have some minutes for questions and discussion. as a summary of what this paper does is I take some basic models of income dynamics, but these are, it doesn't need to be income, but income is my favorite application. And I make them richer by allowing for new forms of heterogeneity. The difficulty here is the heterogeneity enters in a nonlinear way, and then if we want to use traditional identification and estimation approaches, they don't work anymore. So what is good about the identification argument here is it's quite general. We just need to arrange the data in the future, past, and present, and find the right numbers of instruments and so on. But once we get this, then we can just carry on the identification argument, and we can identify particularly the distribution of heterogeneity. This applies in this HTR model, but it applies in other models that are of interest, for example, heterogeneous autoregressive coefficients or heterogeneity in the variance of permanent shocks. These are all possibilities as well. And in terms of the empirics, one of the messages of this paper is there is substantial inequality in the amount of transitory risk that people observe, and this cannot be explained at least by the most usual exogenous covariates like age and education. It's not just a story of age, education, life cycle, and family composition. There are other things that make people different for long periods in the amount of transitory risks that they face. This is important for a variety of questions, as I said, the understanding the effects of different policies and doing welfare calculations certainly is something that must take this into account. And if we want to construct a quantitative macro model and we want to calibrate the income distribution, we need to also allow for these heterogeneity in risks. This is, I think, one of the practical messages of this paper. There is this heterogeneity there, and moreover, one could take the estimates that I get and just calibrate a distribution and input this into a macro model. So one last point here is the messages of this paper connect quite easily or interact quite easily with other areas of economic analysis. And having said that, yes, well, thank you for your attention, and I'm open to questions and comments.
Yeah, I have one question, Tincho. Just to understand your last experiment, could you come back to this slide, to the consumption and the previous one, this one? So if I understood correctly, what you're saying is if you like to do an exercise similar to Blandel, Pistaferri, Preston, first of all, in your environment, you're gonna need to change the definition of the transitory shock. They have a transitory shock that is not this epsilon hat, because here this epsilon hat is, if I understood correctly, is the transitory shock divided or normalized by the idiosyncratic variance. Is that correct?
So I would interpret it in the other way around. I'd say they are. It's not to demean what Blandel, Pistaferri, and Preston did, but I'd say they inadvertently had this sigma I there, but they just run a regression, which is not exactly what they did in GMM, right? But it's equivalent to running a regression without using as an instrument the sigma I epsilon IT, because they were not assuming that the sigma I was there. So that's the sense in which this was inadvertently using an invalid instrument, because this sigma I epsilon IT has the sigma I that might be correlated with something in the zeta IT. That would be and then what I do is I use the epsilon IT, not the sigma I times epsilon IT as the instrument. It's more complicated than that, because you have to do variances and covariances, and but this is the intuition of why there is the bias there.
Yeah, but my understanding is if you are able to recover, you give me the persistent shock, the transitory shock, that is epsilon, and the idiosyncratic variance of the transitory shock. When you run the regression, which elements you want to consider? The permanent shock, And the transitory shock but complemented or augmented by the idiosyncratic variance.
Yeah, that's I think, yes, I think these are two different questions. One is the endogeneity bias, right? Well, here we have the epsilon IT because we don't believe there is a sigma IT, although it's there.
Mm-hmm.
And we use it just as this is like an endogeneity bias. Endogeneity would come from some fixed effect in the zeta IT, right? But the other question is, do I want to regress on the epsilon IT tilde or the epsilon IT? It's not clear what we want. I did the epsilon tilde IT for comparability because I want because my interpretation is the average response of consumption to changes in transitory income with the same scale as in the BPP exercise. If I do here the epsilon IT instead of the sigma I times epsilon IT, I will get a different weighted average of the consumption responses. Right? That would be the. So I thought this was more comparable, but I can certainly do both. Right?
Because in case you would like to do a regression, just taking into account epsilon, the transitory shock, this is not gonna, you're not gonna get any bias. This is because there is no endogeneity. This epsilon is uncorrelated with everything, and you're getting the marginal effect of a transitory shock without considering this heterogeneity risk on consumption.
Yes. Yeah. I think both can be justified, like regressing on epsilon tilde doing the IB or the IB-like thing, or regressing on epsilon and doing the OLS, just because in that case there is no endogeneity. Both could be justified. The thing is, because BPP got as 0, this is something about scaling that shouldn't matter for the comparability, right? Actually, both. I mean, I didn't present the results for the epsilons, but it's also a positive number. It's not exactly the 0.18 that it was there, but it is a positive number. So this is yes, these are two different ways of measuring. I mean, at the end of the day, we want the average here. This regression is actually not the most ambitious quantitative exercise that we can do with consumption. We would like to get something like the policy function or things like this. Here we have to decide how we weight the average of consumption responses, and we could go one way or the other, right? We could weight them by the sigma I or not. That's kind of the choice here.
Great, thanks.